fairly easy one, but you don't want to like get behind and try to learn too much at once. It's basically just 4 formulas. We have 2 formulas before the quiz and then 2 formulas after the quiz, which is why it's also a very short unit. Like, a lot of just like set up and then find the answer. Quiz this unit. Again, it does come up quick, but again, it is a very short unit anyways with not a lot of topics, especially compared to the one that we just did. But your quiz will be on Friday, and then the test is on the following Friday. I know that's one of the virtual days, but this test, I'm honestly fine with it being virtual for everyone and probably a shortened period, because this test is never a long test. Like, it never takes a full class period, just because there are not a lot of topics that has to be tested for the unit. What this unit covers, though, is basically area and volume, how we use calculus, specifically how we use the integral to find the area of any shape or the volume of certain types of 3-dimensional figures. So to start off with the notes, this slide is in your OneNote, but I did want to go ahead and kind of talk about why this works so we can kind of develop a formula for it. So when we're talking about the area between 2 curves, we are going to be asked to find the area bounded by graphs. It could be 2 graphs, it could be 1 graph, it could be 3 graphs, but we have some region that we're trying to find. So like in this one, we will be trying to find, and I made it so you can kind of drag it around. That is the area that we are trying to find. Well, we already know one thing about area in calculus. We know that the definite integral is just the area from the curve, but all the way down to the x-axis. If we're doing the area between 2 curves, well, clearly we're not going down to the x-axis, but I think it is pretty logical of how you can kind of find that area. For example, that red graph, here would be its definite integral. Again, that would be its area from the curve down to the x-axis. So we would have that overall area. And if I want to find the yellow region, I would have to subtract off the area underneath that purple curve. And so basically you're going to have like this bigger area minus a smaller area. And then what's going to be left over is that area between the 2 graphs. What's going to be important in this unit, we will do kind of half of it with a calculator, half of it without a calculator. When we do problems without a calculator, sometimes they will give you the graph, sometimes they won't. At the top of the notes, you'll see this graph prereqs page. This is basically all the graphs any student in AP Calculus should like already know how to do. So it's like your basic parent functions, the linear function, the quadratic one, the cubic one, radical function, and then like transformations of them. So like anything that's a very basic graph, you should know how to graph it without a calculator because it is a basic graph. Let's go ahead and look at an example. And we're going to start off doing things no calculator, and then we'll look at some examples with a calculator. So I have 2 graphs. I did color code them, but again, we should be able to tell which graph is what because we understand transformations. F of x, that blue one, has the negative x squared, so I knew it was going to be a downward facing parabola. And then that g of x is the red one, positive x squared, so I knew it would be like that upward facing parabola. What are we trying to find? When we say let's find the area defined by that region, enclosed by that region, that's going to be this shape right here. And I want you to kind of imagine why the calculus might be important. That yellow shape is not like a shape we have a geometric formula for. Like it's not a trapezoid, it's not a square, it's not a circle, it's just some weird shape bounded between 2 graphs. Well, the idea behind it, if I want to find that area, we want to think about, okay, let's find this like total area and then subtract the part that we don't want to include. What would be the total area? That would be this blue region we have. That would be the area underneath the blue graph. And again, we could use that with a definite integral. We know the area from, the definite integral from a starting point to an ending point gives you the area from the curve to the x-axis. So once we find that area, how would we finish out that problem? We would want to subtract out from it the area that we don't want to include. So I would subtract off the one from the red graph, and then that answer would give us the area that we're looking for. So again, if I'm looking for that yellow one, and again, if I want to think about finding the area of it, we're first going to have the area underneath the blue one. And again, that's going to be from a definite integral. I'm gonna put like a dx at the end. Let's go ahead and write the definite integral. Looking at that shaded blue area and kind of where it came from, where is that area starting at, what x value? -4, so it's starting at -4. Where is that area ending at? 2, so it's ending at 2. What are we trying to find the area of? That top one, 8 minus 1/2 of x squared. And then what are we going to take away from that? We want to subtract what I have the graph underneath the red one, because that's not including the yellow region. So I'm going to subtract from that. It also starts at -4 and ends at 2. What's the area underneath that red one? Well, you just want to integrate that red graph with respect to dx. So we basically have like a larger area minus the area we're not including. Whatever that number is would represent the area of that shaded region. Now there are ways we can simplify our answer. Like both of these have the same limits of integration. They both go from -4 to 2. So you can write it as a single integral from -4 to 2. There is the upper function minus the one underneath it. And then dx at the end. That's basically what we're going to focus on today. Like clearly we're going to look at a lot of different examples. But the idea in this first topic is we want to be able to find the area between curves, 2 or more curves. And that's going to be basically the setup that we're using. Now I said this unit is very formula based. I think it's also like very like logical based if you think about it that way. But I do know y'all like a good formula. They're just like a formula to memorize and use it. If I were to take this and put it as a formula, this is how I would write it. So I do have it written 2 different ways. The first way is kind of like the original version of it and kind of where the formula comes from. And I'm going to think of it as like the top function minus the bottom function. So again, if I want to find the area between 2 curves, I think about finding the entire area underneath the upper function, the top one, and I'm going to subtract from it the area underneath the bottom function. What will be left over? Obviously the area in between. It's going to be a whole lot easier for us, instead of writing it as 2 separate integrals, to just write it as a single integral, since it will have the same starting point and the same ending point. One fact, just to kind of write down, then we'll look at an example and actually calculate it, but the area between curves for us is always positive. Which I guess is nice. You don't have to worry about like moving backwards on the integral or what happens when it's below the x-axis. When we talk about finding the area between 2 curves, it's always going to be a positive number. Yes, Evan?
So you have the area between the blue and the red, with the blue on top and the red on the bottom.
Uh-huh.
You go past 2, x equals 2 a little bit, you have red on the top and blue on the bottom.
So when I say area between curves, it's going to be like some bounded area.
Yeah.
But what you're asking, like say if I wanted to find the area and you're imagining, like for an example, just like extending it,
Yeah.
and maybe wanting to find the area of like that deformed fish type shape,
Yeah.
then you'll basically do like 2 integrals. So you do like the area of awkward football and then the area of like the awkward triangle. And they have different tops minus the bottom.
Yeah.
And that's one thing we'll pay attention to, is like making sure the top function is always the top function
So
and making sure the bottom function is always the bottom. So yeah, we would separate it in that case.
And at that point, would the red be the top?
Yes.
Okay.
And we have some where we'll do that. But let's go ahead and start with a pretty simple one. I left kind of a similar shape, but I chose 2 functions that were a little bit easier to deal with. So I have y is equal to 4 minus 1/4 of x squared, and y is equal to 1/4 of x squared minus x. And we want to find the area between those curves. So that region I have shaded in that purple color, we can find that exact area. Which again, imagine how powerful that is. We can no longer bound it behind the area of just like basic geometric shapes. Like literally any shape that you can kind of write a function to match its size, we can find the area of it. When I'm doing an area problem, before I do anything, I kind of just do like an empty integral and then just kind of fill in what I need. So we're going to have like a top function minus the bottom function Don't leave your dx at the end of it. And then kind of fill it in. Top function minus the bottom function. Looking at this one, what's going to be the top function? The red one, so that's going to be the 4 minus 1/4 of x squared. What is going to be the bottom one? 1/4 of x squared minus x. And again, you do want to check that red one stays the top function of that region, that blue one stays the bottom function of that region. That's the first part of your setup. We also will have to have numbers on our integral sign. We want to say like where this region is starting at and where this region is ending at. How are we going to find where this region starts at and ends at? It's the intersection point, so it's where the graphs intersect at. How do we find the intersection points algebraically? Set them equal to each other. So honestly, to be completely honest in this unit, I often find the mistakes not in the calculus, but in the algebra of like solving the equations. So we basically want to find we want to find where this area starts at and where does it end at. That is occurring at the intersection points. How do we find intersection points in math? We are going to do this one all by hand. So we're going to set them equal to each other. Marcus, you had a question. What was it?
Yeah, so when you're in the integral, could you combine like terms?
You can. So when we actually evaluate this one, we'll simplify it first. Yes, Hermione.
We always like, you gave us one red and one blue, so we know which one is which. But we have to identify.
Good question. So like if this was the AP exam or my test, I would print it in black and white. And how would you identify which is what? That red one is 4 minus an x squared. If I see negative x squared, that's going to be a downward facing parabola. So if I didn't color code it, we should know kind of what functions look like to match it up. Or it would be a calculator question. You can graph it to figure out which one will be the top and which one will be the bottom. Yes, David?
So they give you the two equations and there's no graph, it will be a calculator question?
No, it could be a no calculating one.
And how would you know which one's on?
You would just have to know what the graphs look like. And that's where those prereq skills are important.
Okay.
So they're not going to give you one where it's like, so you have the blue graph. Let's just say like you like move it up by like 2, and then those are your 2 graphs.
I mean, sure, why not? I could. We can find the area between any 2 graphs. You just rewrite the function.
Okay.
Probably not without a calculator, that'd be harder to solve.
Yeah.
But let's go ahead and finish kind of this one out. We do want to be able to solve that equation. I don't like dealing with fractions, so what can we do first if we're trying to solve that equation? Multiply by 4. Let's just go ahead and get rid of the fractions, make it a little bit easier to solve. Multiply everything by 4. I say I have an x squared and an x term, so how are we ultimately going to have to solve this one?
Oh, factor.
Factor, right? Which makes sense. We have 2 intersection points, we better get like 2 x values. So I'm going to go ahead and get one side equal to 0. Doesn't matter which side you get equal to 0. I'm going to go ahead and add x squared to both sides. That negative 4x is fine. Subtract the 16. And then solve it from there. So I'm going to go ahead and factor out that 2. And then factor. 2 numbers that multiply to give me negative 8, but add to give me negative 2. And now I can use 4 and 2. And I want the 4 to be negative and the x positive. So solving that equation, I get x is equal to 4 and x is equal to negative 2. Again, what was the whole purpose of doing that? When you set 2 graphs equal to each other, you're finding the intersection points. So those x values we found, those are the points of intersection, the x coordinates. So it's crossing when x is equal to negative 2 and when x is equal to 4. Where did those numbers go? Always go in order because the area between graphs is always positive. Going back to my integral, and I'll scroll over in a second, this area starts at negative 2 and ends at positive 4. Questions so far? All right, so let's go ahead and talk about this answer. I'm going to zoom out so we can see all of it on a page. We set up our integral. That integral represents the area between the 2 curves. We're done with the new stuff. Now we just have to actually find that area. How do I find that area? I just want to evaluate that integral. Before I find the antiderivative, going back to what Marcus asked earlier, I would probably simplify this. Instead of having 4 terms, I do see there are some like terms to combine, just to make it a little bit easier for me. So this is the integral from -2 to 4. I have 4. Making sure we distribute that negative. That's going to become a plus x, -1/4 x squared, minus another 1/4 x squared, if I can talk, is going to give me -1/2 x squared dx at the end of it. And then from here, it's just going to be your basic definite integral. Find the antiderivative, and then plug in the top number minus the bottom number. Antiderivative, that's going to be 4x plus 1/2 of x squared, minus, that's going to become x cubed. 2 times 3 is 6, and then plug in the top minus the bottom. Plugging in the top, I have 4 times 4 plus 1/2 of 4 squared minus 1/6 of 4 cubed, minus, plugging in the bottom, 4 times -2 plus 1/2 of -2 squared minus 1/6 of -2 cubed. I'm fine if you leave your answer like that. I do know what this is equal to because it's the 3rd time I've done it today. It does simplify to give you 18. You can double check me, but it's going to be 18. And again, I do want you to kind of imagine like what we found. The actual area of that purple region is 18. I sometimes find students like, I don't know if astonished is the right word for that, but just like not what is expected. Like you're used to seeing like what's the area of a rectangle based on height being like a nice pretty number like 18. You're used to things with curves in it like a circle, pi r squared, not going to be a nice number because that pi in there. But there are lots of shapes, like this is just some irregular shape defined by 2 curves. It does have like a nice area that's exactly 18 units squared. But that's general kind of how you would do this problem. Like set it up, find the antiderivative, and then plug in the top minus the bottom. Questions on that problem? All right, second question, which is actually going to go to kind of what Taylor asked. What happens when you don't have a graph? And if you don't have a graph, surprise, you get to just figure out what the graph looks like on your own. And this is when having those good, strong prereq skills are going to be important. Any graph you've ever learned in math can show up. Polynomial ones, trig ones, log, exponential, lines, they can all show up. So I have find the area of the region enclosed by e to the 2x, y equals to e, and x is equal to 0. This is a very visual topic. Like you need to see what is the top function, you need to see what the bottom one is, but you don't have to draw a perfect graph. And so this would be a no calculator question. Let's go ahead and just try to figure out the region. Let's do the easy one first. X is equal to 0. We all know what that is. So x is equal to 0 is going to be what line? The y-axis. So we know there's like a boundary of the border we're looking at. Let's do the other one I think is pretty easy, I hope. Y equals e to the 2x is what type of function? Exponentials, the people in front of me are doing a little swoop with their hand. We know what this looks like, exponential function. It gets a sketch, not perfect, but you might be able to find this y-intercept pretty easily. Just make sure you draw it accurately. When you plug 0 in for x, you get e to the 0th power, which is going to be 1. So we know this is crossing at 1. And then we have this weird one, y is equal to e. E is a constant, like pi. Anyone know what e is approximately? It's 2 point something, that's good enough for us. It's 2 point something. Well, what does y equal a constant look like? Straight line, that is horizontal. And it's 2 point something, so bloop, it looks something like that. What are we trying to find? We are trying to find this area. Again, if I'm doing an area problem, I just do kind of like an empty integral and fill in things as I identify them. So I'm going to have the integral, top function minus the bottom function in terms of dx. So let's go ahead and fill it in. What is the top function of that region? Y is equal to E. So it looks weird, but E, that is the top function. What is the bottom function of that region? Y equals 2x. And again, that is the bottom the entire time you're looking at that region. And then you're like, well, x equals 0 is also a boundary, but where does that 0 end up showing up at? On that integral sign, right? Where does that area starts at? It starts at 0. So we only really have one more thing to find. We need to find that top number of the integral sign, which is going to be where the region is ending at. How do we find what x value that region is ending at? Set two of them equal to each other. So this is going to be the top and the bottom equal to each other. So I will want to find when y to the equals e to the 2x is equal to just e. Don't make that harder than it needs to be. If e to the 2x is equal to just e, or maybe easier to see it, e to the first, what would x have to be equal to? 1/2. So again, don't make it harder than it needs to be. And that would be the top part of your integral. That integral will give us the area of that shaded region. So now, like, the new stuff is over. Now it's just old calculus stuff. Find the antiderivative, plug in the top, minus plugging in the bottom. Let's go ahead and find this antiderivative by hand. E is a constant, just like 2, 3, and -6. So what's going to be the antiderivative of E? EX. Looks weird, but E is a number, so its antiderivative is just going to be EX. Minus, now we want to integrate the function e to the 2x. Let's remember some rules. The integral of e to the u is e to the u. That does have a 2x up top. So what rule do we also need to use?
Chain rule.
U substitution, what we use for integrals. Opposite of chain rule, yes. So again, like u would be 2x, u prime would be 2. What coefficient is going to go in front of that term? 1/2. 1 over u prime, and the integral of e to the u is just e to the u. And then making sure you plug in the top minus the bottom. This one's also pretty neat. Like, it looks like an ugly antiderivative, but it actually simplifies pretty nicely as well. So let's go ahead and plug in the top minus the bottom. Plugging in 1/2. 1/2 e minus 1/2 of e. 2 times 1/2 is just 1. So that's just going to give us e. Minus, plugging in the bottom, I have e times 0 minus 1/2 of e to the 0th power, 2 times 0. Simplifying it, cancels, distribute the negative. What is the area of that shaded region? Just 1/2. Again, I think it's neat. I'm also a calculus teacher and kind of a dork, but that kind of irregular shape we have, its area is exactly 1/2 units. It is not a triangle. It's related to triangles in some ways, but it does have an exact area of 1/2. Questions on that? All right, so we did one where it was no calculator and we have the graphs. We have one where it's no calculator and no graphs. Third type of problem is going to be a calculator one, everyone's favorite. Yes.
Can you go back just a quick second? So you put EX. Are you able to put the X in front?
Yes.
Okay, it doesn't really matter.
It wouldn't affect it, no. So let's go ahead and look at this one. And those of you at home, I'm going to reshare my screen so you can see my calculator. And again, just double check that you're also in radian mode, of course, while you're in this class. There we go. So, calculator problem. The short version of it, we need to graph it. We want to see the graph so I can see the top function, so I can see the bottom function, and then also use my calculator to find those intersection points. Let's just go ahead and get some things out of the way to make sure we're kind of clear on them. Your final answer has to be exact to 3 places. those intersection points are probably gonna be at ugly decimals. So when you find the area, you want to make sure you use more decimals when you plug it into your calculator so that your final answer doesn't end off by too many decimals. But pretty much we can do everything we need to do in the calculator. So I'm gonna go ahead and graph them. So I'm gonna hit y equals and type them in. Of course, those are already typed in for me since I have done that already today, but I'll give you a chance to kind of follow along. I am also going to, as we do this problem, just remind you some shortcuts, like how we save like intersection points in the calculator, just so we don't have to do as much typing in the long run. But you do want to go ahead and graph them. Zoom 6 will give you a window that works. And like if you hit Zoom 6 all day long, that's probably going to be fine. Personally, for me, I like being able to zoom in a little bit more just to see that region a little bit more clearly. And you can do it by hitting zoom in, or I just kind of like fixing my window directly. So like I'm just in the first quadrant I kind of see and kind of close to the origin. So I'm just going to change my X max to like 5 and my Y max to also like 5 and making the minimum like -1. Again, that is just personal preference because I like being able to see it just a little bit more clearly. So we're trying to find that region. If I'm doing this on like a piece of paper, I would probably just draw like a quick sketch of the graph. And then we do want to be able to identify the top function and the bottom one. If you have a color calculator, it's going to be pretty easy, but also just as easy if you have one in black and white. Like if you hit trace, and whichever one the cursor is on, it will show you at the top of the screen which one's being highlighted. This one is my Y1, which I saved as f of x. And then I see that if I trace down to the red one on mine, I see that that is the 3/2 to x. So I know my top one is f of x. And my bottom one is g of x. What am I trying to find the area of? That region in between them. So I do need to go ahead and find my intersection points. Again, let's review how we find our intersection points. I'm going to hit second trace or second calc, intersection. It will ask you questions. What's your first curve? Yep, that's it. What's your second curve? That's also it. The guess is important because you'll often have more than one intersection point. The one your cursor is closest to will be the one that it finds. And I always like working from left to right. So I scrolled over to the one on the left and then hit enter, and it tells me my intersection point. If you're doing this and you don't want to store values in the calculator, I would recommend writing down that intersection point to as many decimals as you see. And I am calling it A. And the reason why you want to do this is when you go to plug it into the integral, you do want it to be an exact answer in the final step. So that's going to be 0.118. 0468.
How do you get the exact intersection point?
I'll do it again when we find the second one. And then another option is if you want to save it. So that's going to be fewer options, like less typing in the long run. Immediately after find that intersection point, you can hit second quit, type in X, the store button above on, and then whatever letter you want. I'm going to do alpha A, and then enter. And now my calculator has memorized that the variable A is that first intersection point. So let's go through those steps again, but for the second ones. I'm going to hit second calculate. I need to find an intersection point. It will ask me questions. What's my first curve? Yep, that's it, enter. What's my second curve? That's it, hit enter. Guess. Now I'm going to scroll over to that second intersection point. Enter. And then I either want to write that down so I can plug it into my calculator again, or save it in my calculator. How do I save it? Second quit, X, store it. I don't want to overwrite my A, so I'm just going to do alpha B, enter, and it will save it. So I know that this area is going from that 0.118 to 2.198, and I'm going to write some extra decimals just so my final answer doesn't end too far off. And now we want to go ahead and just set up the integral. So we are still finding the area. How do we find the area? That's going to be the integral of the top function minus the bottom one. And again, I found that was the top one. And this was the bottom one from the calculator. Where's this integral starting at? It's starting at 0.118 and ending at 2.199 if I round. Again, huge disclaimer, always want to show your setup. And notice in my setup, I just rounded the 3 places. But when I actually find the area, I need to make sure I use more than 3 places, or there's a high likelihood my final answer will be too far off. Why I like saving it is so I can type in less in my calculator. So I'm going to hit math 9. I can type in the 0.1180468, or I saved it, so I'm going to hit alpha A. And then the top one, I could type in that 2.198968478, or just hit alpha B. And then the other option, I can type in the function. A lot of students just like typing in the function again. I don't like doing things that I've already done, so I'm just going to select it by hitting vars, yvars, function. My top one was y1, and then my bottom one was y2. Vars, yvars is a function, and then y2. And this is in terms of dx, and then enter. What is the area of that region? Again, rounding the 3 places, 2.959 would be the area. The other way you could have written your answer, so if you wrote down A is equal to all of that and B is equal to all of that, you could have shown this as your setup and literally wrote this on your paper. And then, of course, what it was equal to. And as long as you wrote this somewhere on that page, that final answer I wrote in black would be perfectly acceptable because you have to find A and B, and you wouldn't have to write those decimals over again. As long as, even like an AP grader could somewhere see where you defined what A and B was. Taylor, your question.
Just how do you get to y1 and y2? Like,
Once you type in to get to it, you're going to hit vars next to clear, and then it's a y variable.
Oh.
Any other question on that one? All right, almost done, I promise. And I know you're so ready for a long weekend. 2 more slides, and then we'll be done. Go ahead and look at this one for me. Again, we'll do this one on a calculator. But it says try to find the area by integrating WRT. I'm going to let that be the abbreviation for with respect to x. We'll have like the dx in our problem. This one's unique because that region is bounded by how many graphs technically? 3 of them. One nice thing, and we'll see this a lot this unit, I use it on my quizzes a lot, it will tell you sometimes just to set up the integral but not evaluate. Be happy for those problems, you just have to like set it up and move on to the next one. So your answer just needs to be an integral. This kind of goes back to what Evan was asking earlier in the class. If you're looking at that region in yellow, and you know you want to go ahead and set up an integral, and you start looking at the top function and then the bottom function, what do you notice that's going to cause some issues for this particular graph? That top function is not consistent. So like you're looking at it kind of from left to right. This first part of the region, the top function is the red one, the bottom one is the green. Right here at 3, you can kind of see it flips. The top function is now the blue one, and the bottom one is now the green. You want to be careful with problems like this, because how many integrals are you going to have to set up to find the area for that entire region? 2 of them. You're going to have one for that kind of left side, where the red one's on top, and then you're going to have a separate integral for the one where the blue one is on top. Thankfully, it tells us we don't have to evaluate it. We just want to write an expression that would give us the area if we had to evaluate it. So let's go ahead and just start it. I like working from left to right. Where's that first region starting at? 0. So again, make sure you use x values. It starts at 0. Where is it ending? 3. And then we're going to have the top function minus the bottom function. Don't forget your dx. The top function is the red one. What is the bottom function? That green one of negative square root of 4 minus x. That's only part of the region. That is only on this side of 3. So then if I want to finish that problem, we have a second region, so plus. Where is that second region starting at? 3, and where is it ending at? 4, and then we still have top minus the bottom in terms of dx. Its top function is the root 4 minus x. Its bottom function is the negative root 4 minus x. Looking at this, hopefully you can kind of look at this and be like, this is one that we are glad we don't have to do it by hand. That's just going to be a lot of tedious work. Like you have 2 integrals, some not so fun derivative integrals to find with that root 4 minus x. Some simplifying, but really that is all you can do. This does represent the area of that yellow region. My proposal to you is that a problem like this is actually easier to do if you imagine like tilting your head to the side and doing it in terms of dy instead of dx. So before we move to the last slide of the notes, when you're doing a problem that is with respect to dx, and you see that dx at the end, that means every single thing has to be an x value. What do I mean by that? The numbers on the integral sign, those have to be x values. The functions you plug in have to be in terms of x. And then, of course, you have dx at the end. So literally everything has to be x values. The easier way to do this problem, we'll see kind of why, is to actually kind of flip it around and do it in terms of y. Evan, you had a question?
Yeah, so about that, like, sideways parabola,
Mhm.
like with respect to y, so if it's specified with respect to x, it's like very.
Yes, so often they won't tell you which one to do it to,
Okay.
and you get to pick which one is easiest. Yes, Armani?
For something like this, we would have to like find the numbers on the integral, right?
No, this one, well, I assume this one was landing at nice whole numbers. You could solve this one if you had to by hand. You'd probably start off by squaring both sides. But this one, we assumed it was landing on whole numbers. Let's do it in terms of y, and this is where we're kind of going to finish up today. So same graph. This one is easier to do in terms of y. And again, when I say something in terms of y, it means everything we see has to be a y value. Let's do the easy part first. If I am proposing that we can do this in terms of y, what will be the starting and ending y value where this region is starting and ending at? -2 to 1. So again, we're using y values instead of x values. And it's going from -2 to 1. Still going to have a top function minus a bottom function in some ways, but we are going to look at it a little bit differently. Let's talk about how we can get these functions to be in terms of y. Right now, these are functions of x. It's y is equal to blah, 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 bunch of x's. I think the line is going to be the easiest one to think about. Y equals x minus 2 is the graph of a line in terms of x. If you want to put that in terms of y, what do you think the equivalent line would be written as? Y plus 2. So basically solve it for x. If y is equal to x minus 2, then x is equal to y plus 2. What's unique about this one, if you do it in terms of y, those two, the blue graph and the green graph, basically are the same equation. Why is that true? Let's kind of think about solving it. I'm going to do the blue one first. Y is equal to the square root of 4 minus x. Solving for x, what would you do first? Square both sides, so you have y squared is equal to 4 minus x. Then solving for x, I'm going to add x, subtract the y squared. So I have x is equal to 4 minus y squared. Looking at the green one, it was y is equal to negative square root of 4 minus x. Well, if you square both sides, what's happening to that negative? It goes away. It turns to a positive. So you end up with that same y squared equals 4 minus x, which is the same graph. Not sure how much you remember from pre-calculus, but conic sections might ring a bell. Anything that is like y squared, that's basically a horizontal parabola. So that graph, x equals 4 minus y squared, is literally this entire graph by a single name. Again, this unit I think is very logical if you think about it. So when we were in terms of the x, we did the top function minus the bottom function. If we're in terms of dy, how do you think we're going to figure out which two we're subtracting?
Left to this right.
So which one will be the bigger one, the left one or the right one? The right one. So kind of think that you're furthest from the y-axis. So you're going to think about it as, if you want a formula, the integral from a to b of right minus the left. And that's when you're in terms of dy. What is the right function? That's that horizontal parabola, which is 4 minus y squared. What is the one on the left? That would be y plus 2. Notice if I'm doing it in terms of dy, everything I put down is a y value, the function and a number on the integral side. Comparing that integral to the one on the previous slide, if you had to find one, that integral is way easier than the one with all the square roots in it, and we had to use just one integral versus two. That is where I'm going to stop at today. Classes kind of running towards the end. On Tuesday, after the long weekend, I basically have a short warm-up, like you can see it in the notes already, where I give you like 5 graphs, and we'll talk about which one would be a dy problem, which would be a dx problem if you had to choose. And then just 2 examples to make sure we didn't forget anything over the weekend. The homework that I'm assigning is going to be homework 1. Teams, I guess starting yesterday when there's issues with the virtual test. I don't know what it is about Teams right now, but it's really hating me with assigning homework. Like in my BC class, it copied one homework assignment over 8 times in everyone's notebook. For y'all, you're going to see some homework ones that is locked, and I don't know why it's locked, but there is one that you should be able to find that is unlocked. So sorry about that. I don't know what's happening because I created the assignments the same way that I always have been doing it since August. But yeah, Teams is Teams and it's glitchy. If you can't find the one that you can write on, let me know and I'll try to help you. But there should be a tab somewhere around the Unit 8 tab where there is a homework that is not locked. So yeah, that was fun. That's all I have. I don't really want you spending like a ton of time over the weekend doing calculus. Like I do want you to enjoy the 4-day weekend. Take some time not looking at a computer screen, especially if you're a virtual student. But basically what my plans are next week, Tuesday the notes will be fairly short, and it will be mostly a work day after we finish the notes. Wednesday we will learn our second formula, which is going to be a volume formula. Thursday's a review day, and then quiz on Friday. I know that feels like a really early quiz. It is, but it's literally 2 formulas. We have the area formula and then the volume formula. Other than that, that's kind of the end of class. If you are at home, feel free to hang back and ask any questions if you have them.